Okay, welcome at the review session. You may use the chat box to confirm if you can hear me, and we will start then. Yes, thank you. Okay, that means this is the exam 2 week, exam 2 review session. And as we all aware, the test will be open Thursday and will be closed Monday. That means Thursday, July 5th, and Monday, July 9th. Okay. And I hope everybody has, at the moment, time booked at the examity, because that's quite crucial. And then just the review. We have to just master the concept and take the test. Okay, that's what we have. Thank you. Thank you. Okay, that's from after midterm 1, between midterm 1 and now, what we cover. We did cover last section in chapter 2, which was linearization. That means we may expect question from linearization. And then we did start chapter 3. Chapter 3, we did start with critical values. We remember important points to test the derivative, the second derivative. That means critical points. And then also in the first section, we did have extreme value theorem, finding the absolute maximum and absolute minimum value on the closed interval. Then the next section was about the mean value theorem and the Rolle's theorem. And then the following section was about the increasing, decreasing, and local extreme values. And then concavity and inflection points. And also a limits at infinity and asymptotes, vertical and slant. And I believe everything was wrapped up with the graphing of the function. And the last section was optimization. Okay, that means I kind of line out all of the concept that we have to master. That means let's just solve a few problems which will correspond to each concept. Okay, my first question is, no, I did switch my video off, but okay, that's linearization. Okay, find the linearization L of x of the function x to the power of 3/4 at 16. Okay, that's we remember linearization is just the equation of the tangent line, but we did use that form, f of a plus f prime at a x minus a. Okay, and we can see we have the point a 16. We have to just find out the value of the function at 16 and the value of the derivative at 16. But please make the note that this is the linearization equation and it is important. Okay, that means I'm substituting my point a 16, and then I have my number, my function x to the power of 3/4, which will be 16 to the power of 3/4, and then derivative of x to the power of 3/4 is, I can write it down, it's 3/4 x to the power of negative 1/4, which I did copy here. Instead of x, I did put 16. Okay, and now we have to figure out what is the value of 16 to the power of 3/4. I hope we will be okay with this. That means value of the function at 16 is 16 to the power of 3/4, which means the little denominator in the exponent is telling me what root to take, which is the 4th root, and cube means that I have to take to the power of 3. 4th root of 16 is 2. 2 cubed is 8. Okay, that's me done with this. And the same arithmetic I can apply to the derivative. That's mean derivative at 16, it will be 3/4, and 16 to the negative 1/4 means the 4th root of 16 in the denominator. Okay? And the 4th root of 16 is 2. 2 times 4 is 8. 3/8. Okay, I do have 8 value and I have the 3/8. Okay, and then I can simply distribute everything. I can multiply x times 3 over 8, and I can multiply negative 16 times 3 over 8. And 3 over 8 times negative 16, we can simplify 8 and 16, negative 2, negative 6, negative 6 plus 8, positive 2. That means this is the linearization. And that's what I will be looking for. And of course, the point of the linearization is to have a line, to have a tangent line that close to the a value, close to 16, looks almost the same like the original curve. That means instead of taking the fourth root function, I can simply use a line and approximate the value if needed. Okay, let's look at the second question. That means the second question is also about the linearization, but I will ask to estimate a point. That means we do have a few information. F of 3 is equal to 4, and f prime at 3 is 6. Use linear approximation to estimate the value, and we can see close to 0.3, 3.02. That means I will start with the same equation. Everything is happening at 3. Always the a value is like the nice value. Okay? That's not 3.02. The a value is 3. Okay, that means everybody knows this equation, and let's put the values. F of 3 is 4, f prime at 3 is 6, and then 6 times x minus 3. And now what I have to do, I don't have equation of the function, but I know that I have to approximate a value of the function at 3.02. Okay? I did simplify. That means I can say that the value of the function, or let me actually write, first of all, let me write the function. Whatever function we have, we don't have the formula, but the function that we're talking about could be approximated by 6x minus 14 by the linearization. And that means function behaves almost the same, like 6x minus 14, of course, near x3. Okay, that means this is my approximation. Okay, that means I am copying this equation. Instead of x, I will put 3.02, and instead of x, on the right-hand side, the same value. And let's just compute this. I didn't. That's my linearization. One more time. Of course, near, I can repeat this because that's important. Near to x3. Okay, and 6 times 3 is 18, 6 times 0.02 is 12, and 18.12 minus 14 is just 4.12. As we can see, just playing with the numbers, we do have the approximation of the function at this point, having a few information about the function and its derivative. And that means that's also a useful thing. Okay? But again, please start your solutions with this equation. And then everything will like smooth out and you will get your answer. Okay, that means that's linearization. That's the end of chapter 2. Now, chapter 3, and the first thing was critical numbers. That means let's make sure that we understand how can we get critical numbers and what really like they are. Okay, that means I have a few questions that corresponds to this concept. Find the x coordinates of the critical points of the function, and function is defined x plus 4 times cube root of x. Okay. First of all, I will always start with the domain of the function, because we remember critical points are the points in the domain. If some numbers are not in the domain, we can't list them as critical points. However, looking at this formula, x plus 4, I think I can accept all of the numbers, and cube root of x, it's also taking all of the numbers. That means we're not really lucky because all of the numbers are in the domain. That means I can't exclude any option. Okay, and we remember in order to find the critical points, I have to find the derivative and set up, I mean derivative is equal to 0, and then the solution will give me critical points, or derivative must be undefined. Also, if you have this question, critical points, please start with these two equations. Okay, let's find the derivative first, maybe on the side. I think I will use the product rule, right? Because it is product. Derivative of x plus 4 is 1 times cube root of x plus x plus 4, and derivative of cube root of x, I will prefer to have a form. Cube root of x is x to the power of 1/3. Okay, I can write on the side. Cube root of x is the same like x to the 1/3, because it's easier to use the power form and see actually the power form. That means derivative of this will be 1/3 x to the power of negative 2/3. Okay, let's clean this values. Cube root of x plus x plus 4 times 1/3, and x to the negative 2/3 means that cube root of x squared is placed in the denominator. Yes, I hope we're okay with this. Okay, I will get a common denominator because I really know the point is to have a derivative in the nice form, and the nice form is most likely single fraction. That means if I have fraction and another term, it's nice to combine everything together. That means the common denominator is, of course, 3 cube root of x squared. We did have cube root of x. That means the first quantity I have to multiply and divide by 3 cube root of x squared. Cube root of x squared. Great. And what I have? Now I do have a common denominator, 3 cube root of x squared. And who can tell me, okay, the first question for you, cube root of x times cube root of x squared. What this quantity, if I multiply together, what I will get? Can somebody tell me? It's just x, because this will be cube root of x cubed, and it's just x. Excellent. And then x plus 4. Okay, that means I have actually 2x plus 4. I can write one more time. 2x plus 4 over 3 cube root of x squared. Okay, that means this is a really nice form of the derivative. Okay, that means now I can focus on my condition. Derivative is 0. This is derivative. Okay, derivative is 0, or I can say fraction is 0 if and only if the numerator is 0. That means 2x plus 4 equals to 0. Okay, and then I can solve this equation for x will be -2. But I am just worried because I don't have -2 on my options. Can you see this? Oh, did I make some mistake? 1/3 x minus. You can try to get the derivative, but I don't see any. Yes, that's what oh, I know what I did. Can you see? Okay, who can see my mistake here? What I forgot. I supposed to divide and multiply by the same quantity. I did focus on my cube root. I forgot 3. Okay, that will be 3x and 4. 3x plus 1x. It's not easy to find your own mistake. Okay, that's now I have -1. I think I like better. That you can see how sometimes I think that options, multiple choice options are not helpful, but sometimes they are. You see, they actually they were telling me that I did some small mistake. Okay, that means -1 is definitely in the domain. That means this is a critical point. And also, derivative is undefined. Let's write the whole derivative. because that's what you will do. Derivative is undefined or fraction is undefined if the denominator is 0. That means I have to set this expression to be 0, and this expression is 0 if x is 0, because no other values. And 0 is in the domain. That's also a critical point. That means, Taryn, you write -1 and 0 are the critical numbers. Only -1 and 0. And that's how we can get. But remember these two conditions, 0 and undefined. Okay, I have another one. Oh, trigonometric. Let's do it. Find the critical points for the trigonometric function. And for this one, x minus 2 sine of x, because it's periodic function, we will normally provide this interval, which means this is our domain. I only need a numbers, critical numbers, from that interval, from 0 to 2 pi. Okay, let's find the derivative. Derivative of x is 1, derivative of -2 sine of x is -2 cosine of x. And in this case, the only equation that we have to solve is this one. Derivative is 0. Because no fraction, derivative is always defined. Derivative is 0 if 1 minus 2 cosine of x is 0. I can solve for cosine. Subtracting 1 and dividing by -2, I have half. Now again, question for you. Cosine for what angle is 1/2? Cosine for what angle is 1/2? Of course, the options can help us, but cosine is 1/2 for pi over 6. It's for 60 degrees. It's for 60 degrees. Yes, that's sine. That means 60 degrees will be pi over 3, Zach. Thank you. And we also have first quadrant, and we also have one more quadrant that cosine is positive. This is the first quadrant, and I think the fourth quadrant. That means what will be the like how many times I have to multiply pi over 3 to reach quadrant 4? Or what is the reference angle for the 60 degrees in quadrant 4? I think 5 pi over 3 makes sense, because this will be 300. Yeah, okay, that means we do have 2 points, okay? And both of them are in the domain. That means they are simply a critical points. We don't have to test them. They are definitely in the domain, belongs to, and this is our domain. Okay, that means I see option D works really nice. As you can see, it's not bad because it's testing your unit circle and of course the derivative of trigonometric function and the concept, critical numbers. Next question. Okay, I do have another critical numbers. It looks like, of course, I will not ask so many questions about critical numbers. However, in order to do different things, like finding the intervals of increase, decrease, concavity, we also have to find the critical numbers. That means it's a good exercise. Okay, let's find a critical numbers of this function. 5 times x to the power of 2/3 minus x to the power of 5/3. That means I see 3 in the denominator of the exponent. This means this is cube root. Cube root can take any numbers, positive and negative. That means domain are all of the numbers. Okay? That means again, I can't really exclude any options. Okay, first of all, let's find derivative. 5 times x to the power of 2/3. This will be 10 over 3 x to the power of -1/3. And this will be 5 over 3 x to the power of 2/3. You can, of course, check if I'm doing correctly. I did solve this before the session, but I can it's doing live, it's totally different things. Okay, I think this is okay. This is correct. Okay, now we have to factor out a common factor. Because we remember this from section 3.1. I can definitely see 5 over 3, the common factor. And now, x, we remember, like I can maybe write for you one more time, x squared minus x to the power of 4. What will be the common factor here if we have to factor out? Looking at x squared and x to the power of 4. No? Can you tell me? It will be the smaller value, right? I mean the smaller exponent. And then I will have 1 minus x squared. Okay. That means I have to use exactly the same concept. I will erase this. Okay. And having negative 1/3 and 2/3, the smaller value is negative 1/3. Right? That means only 2 will stay here and 5/3 is outside, but I still need the exponent. That means now, since I kind of like I took away x to the power of negative 1/3 from x to the power of 2/3, that means what quantity will stay here as an exponent? How can we calculate? It's negative 2. Okay, let's see, 1, okay, because what's happened, this number, okay, let me put maybe different color. This number, whatever I will put here, let's say A, okay? A plus negative 1/3, supposed to give me 2/3. That means what number, negative 1/3 plus what number to get 2/3? And I think somebody, Taren, was correct. I think 1. That means we can always think about the properties of the exponent. Just 1. Because 1 minus negative 1/3 will give me 2/3. If I will think about distributing again. Okay, really nice form. Let's get, that means what I have? I have 5 and 3. X to the negative 1/3 is cube root in the denominator, cube root of x, and 2 minus x. Okay, really nice. Derivative is 0 if the numerator is 0. X is equals to 2. Or derivative is undefined, okay, if denominator, not 3, if the denominator is 0, x is 0. Okay, and double check, this is in the domain and this number is also in the domain. That's the critical points, 0 and 2. Well, that means this is the way to get the critical points. Okay, yeah, I think if you understand these concepts, the 25% of the test, you're good. Okay? You can think that you have 25 points. Okay, now, okay, I do have more questions, but I will not solve all of them. I can probably leave it for you and you can practice. But what I can show you, just that's what I was actually thinking for the past problems. Let's see how we can use even more the options. That means, let's see, we have a function and we of course have to find the critical points. Function is x squared, this is no, x squared plus 7 over x plus 3, okay? And who can tell me which number is not in the domain of this function? Which now? It's yes, because denominator cannot be 0. That means x equals to negative 3 is not in the domain. That means, can you see what's happened? Can you tell me which option will be definitely a wrong option to choose as a correct answer? Option A, C, and E. Excellent. That means A, C, and E. Oh, my line is sloping. That's what I was gonna show you. Please also take this as an advantage. If you see the number that is right away not in the domain, just eliminate these options. And of course, BOD, do not guess, do your work, and then get the answer. Okay, that means I will skip this one. And I have another one. I can possibly skip it. I mean, this one is so easy. We can probably see the numbers right away. This one, we're not lucky in like with respect to the domain because cube root can take all of the numbers. That means all of the numbers are in the domain. All of the numbers could be a critical numbers. But we can see how easy we can get the derivative 1/3 quantity to the negative 2/3. Okay, and times, please remember that's the reason that I'm solving just because of the derivative, times the derivative of the inner function. That means this is the chain rule. That means derivative is, I will place 2x minus 2 on the top, 3, and this is cube root of the whole quantity x squared minus 2x squared. Right. And since I can accept all of the numbers, yes, we can probably see the zeros from the top and the zeros from the bottom. That means who can tell me what is the answer? I will try to write it down, but I think you will be first. This is this, and the derivative is undefined if the quantity is 0 and 1. I see the value 2 also. Can you see the denominators? X is 0, x is 2. And all of the numbers are fine. Okay? Zach, do you see also a 2, the x equals to 2? Yes, that means we have to, yes, we have to make sure, but yeah, you will probably. However, you have to be careful because your option is also the option C, which is not, yes, it's not right. We always have to double check. The zeros from the top, zeros from the bottom, okay? But my point for this one was actually the derivative. Please remember about the chain rule. Okay, let's see, probably I have another one. Okay, this one you can just tell me which option is definitely wrong. Can you tell me which option is definitely, the x equals to 1, that means which option I can eliminate right away? And D, yes, thank you. Yeah, you see how nice this is? Okay, that will be and D. And again, we have to find the derivative and 0, undefined, but this is similar to my question 1, I believe. Okay, that means we still have option A, C, and E, but we know that we can't pick B or D. Okay, I will leave this one for you. Okay, that means that's everything from 3.1. Let's keep moving. 3.2 was the mean value theorem. Also, before the mean value theorem, if you remember, I did talk about theorem, just a little bit different. And actually, these two are from the previous sections. The extreme value theorem, oh, maybe this was in this section. Okay, I will still have a question for that. And the intermediate value theorem actually was from chapter 1. But the reason is that I'm listing all of them, we remember, because we do have a common name for these theorems. We call them existence theorem, because sometimes we can just use them to prove that the certain numbers exist. We don't have to like compute the exact values, but we will prove that these values exist. Of course, with some conditions, with some scenario. Okay, let's see what question. Okay, standard question. Find the number C that satisfies the conclusion of the mean value theorem for the function x over x plus 6 on the interval from 0 to 1. That's when we remember the mean value theorem. We always have to remember function must be continuous and differentiable, and it is. It's really important. Function continuous and differentiable, and on the given interval from 0 to 1, and we're not adding the endpoints for the derivatives because we know derivative doesn't exist. Okay, that means just remember this condition, continuous and differentiable. And this is function definitely, this function is continuous and differentiable. Actually, can you tell me what is the number that is not in the domain of this function? You know, what number I can't substitute? Oh, it's -6, thank you, -6. But we can see we do not have a problem with this because we only looking on the interval between 0 and 1. That means we find this function is definitely continuous function. We don't have any breaks, gaps, jumps, or asymptotes. Okay, that means now let's take the mean value theorem. Derivative is the same like the average rate of change, f of b minus f of a, b minus a. Okay, that's again the equation that we have to remember. If you will see the question asking for the mean value theorem, start with your equation. Okay, that means I have to find derivative on the left, and whatever value you will get, that x value will be that c. Okay, that means this will give me, that's the c number. But I will keep x, it's just easier to have x. Okay, I have to find the derivative, quotient rule. Derivative of x is 1 times x plus 6 minus x times derivative of the denominator 1, x plus 6 squared. And on the right hand side, f of 1 minus f of 0, 1 minus 0. And I can possibly compute on the side, f of 1 will be 1 over 7, f of 0, actually 0 over 6, 0. Actually, I can write this because that's also 0 over 6 is 0. 6 over 0, that will be problem. That will be undefined. Okay, that means we do have some cancellations. 6 over x plus 6 squared. F of 1 is 1/7 minus 0 over 1. 6 x plus 6 squared is equal to 1/7. Okay, I can cross multiply. X plus 6 squared times 1 and 6 times 7. Taking the square root of both sides, of course positive and negative, I am getting my number -6 plus or minus root 42. But now I can see I have -6 minus square root of 42 and -6 plus square root of 42. That we can see both negatives are definitely negative number. Okay, that means I can't accept because I can only accept the number from that interval. That means you probably know the answer, but one more thing, square root of 42. We don't have calculators, of course, but we can probably estimate. Square root of 42, can you tell me like the range? The square root of 42 will be greater than a number and less than another number. We can think about the perfect squares. I think 36 and 49. And that means square root of 42 is not equals to, yes, it's between 6 and 7. Thank you. That means it's less than 7 but greater than 6. That means having a number, I'm just trying to, having a number -6 plus square root of 42, this number will be definitely positive because it's greater than 6 but less than 7. That means this is positive, and it's less than 7, that means it's positive but greater than, less than 1. Okay, this number is also less than 1. I'm just trying to check if this is in my interval. It's less than 1. Okay, that's the answer. Both negatives I can't accept because this will be negative number. Okay, that means only with the plus root of 42, not the minus. I'm only accepting this. Okay, but again, mean value here. And lots of calculation on the side. Let's see my next question. Oh, okay. Suppose that function is continuous function on the interval from 0 to 2. F of 0 is 1. And derivative, it's actually between, the value of the derivative is between 2 and 4 for all of the x's from that interval, from 0 to 2. Use the mean value theorem to decide which one of the following statements is true. That we can see, we would like to find out what is the value, maximum and minimum value, like what is the range of the value f of 2. Let's start with the mean value theorem. Derivative, and I can maybe put f of b minus f of a, b minus a. Derivative, and my a and b is 0 and 2 respectively. That means this will be f of 2 minus f of 0, 2 minus 0. Okay, that's mean what I want, what I know this. That means I will use actually this inequality. Derivative is between, this was my just mean value here. Derivative is between 2 and 4. And we can see based on the mean value theorem, I can replace derivative with this value, f of 2 minus f of 0, 2 minus 0. That means f of 2, f of 0, 2 minus 0, of course, is 2. And I believe I have the value for f of 0, and I can isolate in the middle just f of 2, and then I will get the values. Let's multiply each side by 2. Then I will 4 times 2 is 8, and f of 0 is 1. Okay, I'm almost done. I have to add 1 to each side of this inequalities. That means, what is the answer? I'm just adding 1. That means the value at 2 of the function at 2 is between 5 and 9. Between, of course, respecting all of the conditions. Yeah, but we can see what I did. I did replace, right? This was given, and I know that this is the same like this, based on the mean value here. Average rate of change, instantaneous rate of change. Okay, I think I have one more. Okay, I have the Rolle's theorem. Okay, it's also, it's similar to the mean value theorem. However, we have one extra condition. Let me now find the number c that satisfies the conclusion of the Rolle's theorem for the function x times root x plus 18 on the interval from negative 18 to 0. That means it says, okay, the c that satisfies the conclusion. Okay, that's what we will do. I will still check a function. Function is the same condition like for the mean value theorem. Function must be continuous and differentiable. And I think function is continuous and differentiable on that interval from negative 18 to 0, because the values will be defined and no numbers which are not in the domain. Also, the condition, if you remember, okay, I can use this, f of a must not f prime. Values at the endpoints, they have to be the same. Okay, that means I can maybe write function must be continuous and function must be differentiable, okay, on the interval from a to b. And also, the values, they have to be the same. That means let's just check this. Okay, that means value at negative 18 supposed to be the same like value at 0. Negative 18 plus 18. That means what is the value? And 0, 0 plus 18. Okay, I believe the value is 0. That means we find. But please remember, that's the condition. Okay? For the Rolle's theorem, it's additional condition. Okay, and then the Rolle's theorem is telling me that the derivative is actually 0 at some point. Okay, that means this is the Rolle's theorem, which means instantaneous rate of change is just 0, horizontal tangent, just because the values are the same. right? That's they create, if I connect them, they create a horizontal line. Okay, let's find the derivative. Product rule. Derivative of x is 1 times x plus 18 plus x. Derivative of the square root of x is 1 over 2, the same square roots, and times derivative of the inner function, which actually is 1. I don't have to multiply, and this is 0. Okay, I have to just solve this equation for x. Again, fraction and the number. Let's get a common denominator. X will go here, x plus 18. That means I will multiply the first number, multiply and divide by 2 times square root of x plus 18. That means I shouldn't, I have to remember about 2. Okay, let me make a little bit longer. That means 2 plus 18 and 2x plus 18. Okay. And let's see what we have. Maybe I can write here. I will have one fraction with the denominator 2x plus 18, and then plus x from the second fraction, and this one. Can you see that if I will multiply square root times another square root, the square root will be gone, only the quantity inside. That means only the quantity x plus 18 will stay. Okay, did I make any mistake? No, that means now I have only 0. That means fraction is 0 if and only if the top of the fraction is 0. That means I can distribute 2x plus 18 times 2 is 36, plus another x is 0. 3x is equals to negative 36. And I believe this is negative 12. That means this is my C value that satisfies the equation of the Rolle's theorem. And negative 12 is definitely in that interval. Okay. But please remember this, f of a equals to f of b. That's the additional condition for the Rolle's theorem. Okay. Please ask if you have any question, anytime, please ask, okay? I can stop and I can answer your question. That's not, yeah, it's just the live session. That means it's for you. Okay, let's see what else I have. Okay, we can try to do this one. For the given function, x squared plus x minus 5 over x minus 2, which one of the following statements is true? That's mean what we have. There is a number C in the interval from 0 to 1 such that the derivative is equal to, and then we have different values. That's we can see additional thing in this question is that we have to recognize that the question is talking about the mean value theorem. Right? Mean value theorem. Okay. On the interval from 0 to 1. That means I will state the equation f prime of x is f of 1 minus f of 0, 1 minus 0. That means this one is more concept question. We still have to do a little bit of arithmetic, but it's more concept. Okay? We can see there is a number, existence there on the interval. And function is definitely continuous and differentiable on that interval. That's we have no problem. We can apply this theorem. Okay, that means the only thing that we have to find out the right-hand side, because they only want to know what is the f prime at the C number. That's of course the C number. That means let's just check. I have to find, actually, let's find out. What's the value of the function at 1? 1 plus 1 minus 5, 1 minus 2. Who can do the arithmetic for us? And then I need the value at 0, 0, 0, negative 5, 0, negative 2. I can write down this one. Okay, what is this number? Positive 3. 1 plus 1 minus 5 is negative 3. Dividing by negative 1 is positive 3. Okay, 3 minus 5 halves over 1. Okay, 6 minus 5 over 2, it's 1/2. Am I right? We can double check. 3 minus 5 halves, which I get the common denominator, which I don't even have to, I don't like. I mean, it is 1/2, but let me just 3 minus 2.5. Okay, I like this way. I mean, of course, everybody can pick the way. Yes, 3 minus 2.5, of course, is 1/2. Okay, that means derivative is equals to 1/2 at some point on that interval for that function. Okay, that's enough with the mean value theorem. That means you definitely know the condition and you're not gonna miss it on the test. I have another one. We can skip this one. Okay, we have to do this one. This is the extreme value theorem. That means find an absolute minimum and absolute maximum value, the small m and the big M, of the function 4x cubed minus 9x squared minus 12x on the interval from -1 to 1. That means, again, it's a little bit, I mean, it's a concept. We have to understand the concept. And it's lots of arithmetic, and we have to be really careful, okay? Because what is important? Important is that interval. Domain, that's our domain. That means we can only find the numbers from that interval. That means make sure that you're paying attention, because it's so easy to pick the wrong answer, even if you know almost everything. Okay, that means we know that the highest point and the lowest point could happen at the endpoints. That means I have to find the values at 1 and -1, but also could happen at the critical points. I don't know, I will find out the critical points. That we can see, we have to find the critical points and find the corresponding value. And whichever value is the highest, whichever is the lowest, respectively, maximum, minimum. Okay? And we know C is a critical number. That means I need derivative to find C. Derivative of this nice polynomial is just 12x squared minus 18x minus 12. I can factor out 6, 2x squared minus 3x minus 2. And I think I have to find the zeros, because critical points are the values if derivative is 0 at them. That means this polynomial, I mean the second degree, that's the quadratic equation. And I don't know, I will, because the leading coefficient is 2. That means I have to keep 2x and x in order to factor out. I hope we're okay with this. And the last number, the constant, is 2. That means the factors of 2 are 2 and 1. And then if you will think 2x times 2 will give you 4x, which actually I will need -4x plus 1 will give me -3. Yeah, it's additional coefficient that we have to take care of it. Okay, zero product property. X is half and x is 2. That's critical points. Okay, that means now I can put -half and I can put 2. And actually, do you think, shall I find all of the values? Because that's what I was saying, we have to pay attention. Which value I shouldn't really compute? Can you see all of these numbers? That's the x values. Can you tell me all of them are in that interval? No, of course, yes, that means this is the moment, because I believe if I will substitute, if I will get the value for 2, maybe one of them is that value. But no, we can't use it because this is not in my domain. This one is fine. Negative half is fine. But 2, please do not even bother. Don't spend time and compute the value. Okay? That's actually the question. Yes, really, we have to pay attention in mathematics, even if we know everything. Okay, that's me. Let's substitute. Now you will watch me doing the arithmetic. I will substitute -1 to the function, which -1 cube will give me -1, -1 squared will give me positive, and positive 12. What is this number? I believe it's -1. Okay, that's means for -1 we have -1. Okay, it's just a coincidence. Okay, 1, I will substitute 1. 4 minus 9 minus 12. -5, -17. Okay, and let's put -half. -half cube will be -1/8. -half squared will be positive 1/4. And -12 times -half is 6. Okay. What we have, this one is actually half, but I can only divide by 2. 2 over 4 minus 9 over 4 plus 24 over 4. Nice, common denominators. -2, -9, and positive 24. 11, -11, and 24. I think it's 13 over 4. Okay. That we do have a number value -1, -17, and 13 over 4. Which one is the minimum value, the lowest point? I can use, the lowest point is, I believe, this one, and the highest point is the positive number. That means this is my answer. Okay? But please note, this was the main thing on that question. Okay, let's see what else you can see on the test. Okay, let's actually do it because it's the trigonometric, and you will have a little bit of trigonometric. That means the same concept, absolute maximum values, extreme on the closed interval, which is the extreme value theorem, but for different functions, trigonometric. That means we do have function sine 3x plus cosine 3x, and we have to find the highest point and the lowest point on that interval. Okay, and actually, we not even have to compute these values, only the x values. That means only where this happened, where's this occurs. Okay, that means what we have to do, we have to find, first of all, value of the function at 0, value of the function at pi over 3. Yes, that's the endpoints. And this is function. And we have to find the value at the critical point, or maybe points. I don't know how many points we will get. That means let's find the derivative first. Okay, sine of 3x, derivative will be 3 cosine of 3x. Cosine of 3x will be -3 sine of 3x. Okay, and this expression must be 0. 3 cosine of 3x, 3 sine of 3x is 0. Let's divide both sides by 3 cosine of 3x. Cosine of 3x, cosine of 3x, and of course this one, but this will be 0. This will be 0, 3x. Oh no. That means this is 1 minus sine of 3x over cosine of 3x is tangent of 3x. That means tangent of 3x is 1. 3x is my angle. That means tangent, who can tell me, tangent for what angle? I have to copy this 3x. Tangent for what angle is 1? because we need that right-hand side value. Tangent for pi over 4. That means pi over 4, which is 45 degrees, I have to divide by 3. 15 degrees, this will be pi over 12. And I think pi over 12 definitely sits in that interval. That means this is in the domain. That's my critical point. Pi over 12. Okay. And we do have pi over 12, not pi over 3. Okay, but now the thing is we still have to compute these values because we don't know at which is maximum and at which is minimum. That means let's substitute 0. Sine at 0 plus cosine at 0. And then sine, if I substitute pi over 3 times 3 will be pi. Pi over 3 times 3 is pi. Oh, Karen is asking me. Okay, I just divided this equation by 3 cosine of 3x. 3 cosine 3x divided by 3 cosine of 3x is 1. Okay, and then 3 over 3, of course, is gone. That's gone, that's gone. Sine over cosine of the same angle is tangent. Yes, and then 0 divided by anything is 0. And my denominator is not 0 anyway. Yeah, okay. That means just to have different form. Okay, and now if I substitute pi over 12, 3 times pi over 12 is pi over 4. Okay, can you tell me, are you ready to tell me the values? Because I am preparing. Okay, sine at 0 plus cosine at 0. What's the value? 1. 0 plus 1, 1. Thank you. Sine at pi plus cosine at pi. Negative 1, correct? Because it's 0 and negative 1. Okay, and sine at 45 and cosine at 45. I think both of them are the same, right? It's just square root of 2 when we add together. Okay, which one? Okay, can you tell me which option, A, B, C, or D, E, or E is correct? Okay, you can see the maximum number. You can see the minimum. That's which option is correct? D. Okay, let me finish the question. This is definitely maximum, and this is definitely minimum. That means minimum is happening at that pi over 3, maximum at pi over 4. Yes, correct? Let me can see just a little bit of trigonometric. Thank you, Taran. That's good. Okay, that means now I think we've done with all of this extreme value theorems, mean value theorems, Rolle's theorem. Let's look at the graphing. That means what we have to know. We have to know lots of things. Okay, I'm just looking at my graph because I don't have any description, but I know what it is. You're probably also guessing. This graph represents the derivative of the function. Yes, do you remember this? That means just in case if you will have again the same question. If this is derivative, I may ask you like to recover a few information about the function. That means let's maybe find out where the original function is increasing, decreasing, and the local extreme values, where they are located. Okay, and I'm assuming that original function is continuous function. Continuous for all of the numbers. For all x. Okay, that means we don't have any problems to excluding the numbers. Okay, that's what I will suggest. I will suggest to do the test. Okay, we can see that's the zeros of the derivative. And derivative is intersecting. That's the critical points. -4, 0, -2, 2, and 4. And now let's test the derivative. Derivative is negative here, between -4 and -2 is positive, between -2 and 0 is positive, between 0 and 2 is below negative, and between 2 and 4 is positive, and after 4 is negative. Oh, hang on, we have a question. I have a question about this. Is the original function not technically increasing at -2? Yes, at -2 is just 0. For example, because the derivative is 0, it would be either increasing. No. If the derivative is 0, it's the horizontal tangent. I can maybe use that graph. The good example is function x cubed. Right? Because we can see that the derivative of x cubed is this. This is 0 if x is 0. That means x0 is the 0 of the derivative, critical point. And we know the graph, that means at 0, function x cubed at 0 is not really, I mean, it is increasing, but exactly at 0, it's actually horizontal tangent. Here we do have horizontal tangent. Derivative at 0 is 0, slope is 0. Horizontal tangent. Because talking about increasing, decreasing, we never like use the closed intervals. Yes, we always use the open interval. That means we can't really say it's increasing at 0. At 0 is 0 in this case. Okay? That means at -2 is 0. That is probably similar situation, because if the derivative is positive, function is increasing. I can actually write this down. Function is decreasing, increasing, increasing. That means this situation looks like a x cubed. Function is increasing, horizontal tangent, and again increasing. Okay? And then it's decreasing, increasing, decreasing. Okay, that's, you can see based on this test, we will see the intervals of increase and decrease. And of course, we will have local minimum at -4, nothing at -2, local max at 0, local min at 2, and local max at 4. Yeah, that's lots of information. And we remember, yes, like a happy valley, okay? Or the summit, the top of the hill. Okay? That means the green curves, if we will kind of connect it, we will get the graph of the original function. Okay, Taren, you're asking a question. So then it would be from -4 to -2, from -2 to 0, and from 2 to 4. Yes, that's intervals of increase. That's what you just said, saying, correct? It's the same, yes, but you cannot write. You know, it's theoretically you can write it. I mean, what I can say practically. Let's come back to this one. You can see I can say that function x cubed is increasing. That means if this will be just college algebra class, I will say function is increasing everywhere, from -infinity to +infinity. I will not even like point the 0 value and then the horizontal tangent, because of course we need more tools, we need calculus. That means, no, I think you can say from -4 to 0, which of course the point is then you will say that function is increasing at that point. It is increasing, but also it's exactly 0. Yes, and if it's exactly 0, it's horizontal tangent, it's kind of like a still point. We even remember like the question about the moving particle. When the particle is like what are the x values like or t values where the particle is at rest? Derivative must be 0. That means this is kind of like a resting point. Yeah, it's like you kind of climbing, you hit that hill, yeah, that point, but you're still going up. Yes, that means it depends. I think it's both of your answers are correct. Okay? And we will not confuse you on the test. I will probably split this. I will say from negative infinity, from -4 to 0. I'm sorry, I'm just because I'm looking at your answer. From -4 to -2, from -2 to 0. Because I like to make this gap just to indicate that something is happening, horizontal tangent. Okay? If this will be open-ended question, both of your answers are correct. Definitely, all of the mathematicians, they will accept. Okay, let's move on. Okay, that we have to find hang on. Oh, okay. That means the answer, okay, on the quiz, on which quiz? The most recent quiz, the quiz 7. Okay, I can double check. That means I am giving, okay, I will double check. Okay, I will double check. Always, you know, I always do everything for the student's favor. I will not, if I am typing both of the answers and one of the answers is I am marking as incorrect, I will check this. Okay, but I don't. I believe I shouldn't type both of the answers, but I can double check. Okay, that means one of the questions that you can expect is just the intervals of increase, decrease, concavity. That means let's see if we can find the intervals of increase we can get if the first derivative is positive. We know that. Let's find the derivative, quotient rule. Derivative of x is 1 times x squared plus 4 minus x times derivative of the denominator 2x and denominator squared. Actually, let me write this way. Okay, because of course I have to find this, but first of all I have to have good form of the derivative because I need all of the critical points. X squared negative 2x squared will be negative x squared and 4. Okay, that's when I see that my denominator is never 0, because this will never be 0. That means I don't have critical points from the denominator, which actually domain was all of the numbers. But I do have the zeros from the top. Okay, this is 0 if I can maybe solve this way. X is 2 or x is negative 2. But these are the critical points. That means I need a critical points. And now I can test the derivative because derivative must be positive. And this is the good form of the derivative. If I will put negative 3, I will have negative number. If I will put 0, I will have positive and then negative. That means function is decreasing, increasing, decreasing. Local minimum, just in case if this will be the question, local maximum at 2. Okay, that means what answer is good for us? Function is increasing when the first derivative is positive. It's from negative 2 to 2. And we can even see we never include the endpoints. Yeah, that's again, I'm talking about the previous discussion. We never include the endpoints because it's like the function is at rest at that point. Okay, we good with this one. Okay, inflection points. That's me, inflection points. I mean, we have to solve this equation, but we also remember we have to test the second derivative. We can't really assume that all of the zeros of the second derivative are the inflection points. Please also note this, because they are good candidates, but we still have to have different sign. Function must be concave up or concave down on both. Like they have to different concavity on both sides of the number. Okay, let's do it. first derivative is 6x to the power of 5 minus 40x cubed. Second derivative is 30x to the power of 4 minus 120x squared. Okay, and this must be 0. Let's factor out 30x squared, x squared minus 4, and then we have 30x squared, x minus 2, x plus 2. That means this is 0, this is 2, and this is negative 2. That's all of the zeros of the second derivative, okay? But you can probably see, because x equals to 0 came from the even exponent. Always when we have an even exponent, testing a second derivative in this case, the second derivative will not change the sign at 0. That means, let's see if this is true. Okay, we do have 0, negative 2, and positive 2. If I substitute negative 3, we can see what we have. This is always positive. Doesn't matter what I substitute instead of x. Negative 3 will give me negative, negative. Negative times negative is positive. Okay? Then let's put negative 1. Positive, negative, positive. Negative, 3 times, 1 negative. Let's put 1, positive, negative, positive. Oh, something is wrong. No. Oh, no, it's actually good. Okay, it's good because at 0 we're not changing the sign. That's what I said. And if I will substitute a testing value 3, positive, positive, positive. 3 times positive is positive. Oh, no. Again, we have question from Zach. Doesn't matter if the inflection point is not in the domain. No. Also, everything must be in the domain of the function. That means for this polynomial, domain is all of the numbers. Now, it's the same like with the critical points. If the numbers are not in the domain, we're not even considering, we can't name them inflection points or critical points for the first derivative. Okay, that means no, they have to be in the domain of the original function. Correct, they have to be. Okay, let's see. Function is concave up, concave down, concave down, concave up. That we do have inflection point at negative 2, and we have inflection point at 2. Not at 0. But you remember, yes, you remember my session, because I can see right away if the quantity is taken to the power of even exponents, never function will change the sign. And it has happened, negative. That means only negative 2 and positive 2, not 0. That means this is not a good option. Okay, inflection points. Remember this, solve this equation. That's the concept. And of course, test it, but that's the concept. Okay, let's see. Oh, this is a good question. How many points of inflection does the graph of the function f have? And the second derivative is given. Okay, I can maybe rewrite the second derivative. We do have x squared, we have x plus 1 cubed, and we have x plus 2 to the power of 4, but in the denominator. And let's assume that this function is defined everywhere. Okay, because I don't want to exclude any numbers. Function is continuous on all of the real numbers. That's R, all real numbers. Okay, that we can see we also need zeros. We need zeros from the top and we need zeros from the bottom. That we do have 0, we do have negative 1, and we do have negative 2. Am I right? Yes, we do have. That we have 0, negative 1, and negative 2. We have potential 3 inflection points. Do you think you can tell me the answer that it's definitely 3 inflection points, or maybe less? Of course, not this one. All of them will be the inflection points, or maybe some of them will be not. -2 is not an inflection point. Oh, no, that's not a reason. In order to get inflection point, we still need all of the zeros. That means it's something, okay, it's something similar like the critical points. Second derivative is 0 if x is 0 and x is -1. -1. Or second derivative is undefined. That's also an important point. If x is -2. That means actually all of the numbers are the good numbers, assuming that all of them are in the domain. That means we may have an inflection point at all of the numbers. Okay, that means no, it's still the same condition. Right, please remember, because we may have like a corner cusps, then the second derivative is undefined, but still important point. That means that's not the reason. Do you remember what I just said about the exponents? The even exponents? That means which zeros came from the even exponent? Can you see x squared? That came from the even exponent, and -2 came from x plus 2 to the power of 4. That means at 0 and at -2, second derivative will not change the sign. And you can even test it. We can put -2, -1, and 0, and you can test the second derivative. Of course, let me use this one. This will be the formula. This will be the formula to test. Okay. If I put -3, I have negative, positive, positive, negative. If I put -half, positive, positive, positive. No. If something is wrong. See, it's even doing the arithmetic is more difficult. I see right away that that 0 and this 0 is taken to the power of even number. That means we will not change the sign. I will still finish that line. That means only this, add this will be the inflection point. Only one value. Okay, let's do the arithmetic. -3. This will be positive, positive. -3 plus 1 is -3. It's actually negative. If I put, -1.5. I think I put -1/2. -1.5 will give me positive number, negative number, cube, negative. This is -1/2. -1/2 will give me positive, positive, and then positive, because it's, and 1, 2, 3 will give me positive. That we can see function is concave down, concave up, concave up. Only here is changing concavity. Okay, that means please be careful. Oh no, we may have, it's just testing the concept. But we may have all of the numbers in the domain, and suddenly the derivative is a fraction and becomes, that means we may have functions like that. That means I'm assuming that this function, domain of the original function are all of the numbers. But of course, suddenly -2 is not in the, but -2 is not in the domain of the second derivative. Yeah, that means, hang on, why can we assume that the domain is all of the real numbers? Yeah, we may have this situation. Oh yeah, we can definitely have situation like that. Yeah, I mean, the good example is a function, I can maybe write, it's a little bit different, but square root of x. I can have 0 is in the domain, but as soon as I get the derivative, I have fraction. That you can see 0 is in the domain of the function, 0 is not in the domain of the derivative. Okay? That means we may definitely find a function that all of the numbers are in the domain, but taking the derivative or the second derivative later, we will get this. Yeah. That means the derivative, of course, second derivative is not defined at -2, but function could be defined. That's the good example of Things like that. 0 is in the domain, 0 is not in the domain of the derivative. Okay? I know, probably you think that also -2 is not in them, but no. I was just, of course, testing different concepts. But I can definitely tell you that we may find a function that will satisfy all of the numbers in the domain, but this will be derivative. Okay, good question. Yeah, if you like, if you have some doubts and you have some issue, that's good sign. This means that you studying and you almost ready. Good. Okay, let's see. Okay, asymptotes. Oh yeah, you will have a question about the asymptotes. Imagine if the limit as x approaches a number is infinity. Okay, the left. Yeah, okay. Then the function. Oh yeah, that's the explanation of the. It's just an example. Yes, yeah, it's good. Okay, let's do the asymptotes. That means you will definitely have a question about the vertical asymptote, horizontal asymptote, and slant asymptote. That means let's see my first question. Find the horizontal and vertical asymptotes. And actually, I would like to add I did put like a short video about the vertical asymptotes only. That means you can definitely watch. It's on Canvas. Okay, that means you will have maybe better understanding. Okay, horizontal and vertical. That means horizontal asymptotes, we have to find a limit at infinity. Okay, that means remember, for the horizontal asymptote, I will just find how function behaves at infinity. -3. That means, do you remember what is the limit at infinity? Oh, my lines are sloping. Okay, what is this limit at infinity? It's 0. If the denominator is winning in terms of the degree is 0. That means this means that the line, horizontal line, y equals to 0 is a horizontal asymptote. Done. That we can see that's not the option, that's not the option, and probably D is not the option. Okay. Okay, and now we have to find out vertical asymptotes. And do you remember, we have to factor out completely our function. That means we do have, is that correct? This is correct. Okay, that means always factor out numerator and denominator. And then look if you have a common factors. From this function, looks like we don't have the common factors. That means I will not cancel out any of the factors. Now I can see that x equals to -1 is not in the domain, and x equals to 3 is not in the domain. That means that's the potential candidates for the vertical asymptotes. However, if I will cancel them out, please note they will be not an asymptote. But since I'm not canceling them out, they will always stay in the denominator. They will always give me a 0 in the denominator. 0 in the denominator in terms of the limit means infinity. That means I will have unbounded y value, huge value, infinity. That means -1 and 3 are the vertical asymptotes. That means this is a vertical asymptote and this is a vertical asymptote. That's -1, 3, and horizontal 0. Okay? But please do not assume right away. Yeah, always look at the top. Okay, I hope we're learning. Find the vertical asymptote. Can you tell me what is the vertical asymptote? It's 10-second question. I can't simplify. I see the zeros is, oh no, not 0, 2. That means x equals to 2 is not in the domain, and I can't cancel out. That means, yes, this is a vertical asymptote. Good. Oh, okay. No. Horizontal. 0 is horizontal. No. Okay, I didn't ask, but who can tell me what is the horizontal asymptote? It's 1 because the limit at infinity will be, is x over x, the same degree. Horizontal asymptote is 1. Good? Yeah? Good addition. Yeah. Because the limit at infinity is 1. I will not write it down. Okay. Who can tell me a horizontal asymptote of this function? Yeah, they are nice questions about the... no, not -1. For the horizontal asymptote, we have to find a limit at infinity. 1 plus, it is... no, hang on. Maybe I am wrong, but I think it's not 1, it's not -1. What you can do, you can just split. You can think limit of the constant is just constant. That means limit of 1 is just 1. And then what is the limit of this part at infinity? 2x plus 1 over 1 minus 2x. Right? What is the limit at infinity of this part? It's -1, right? That means what is 1 plus -1? Yes. And this is a horizontal line, 0, and that's the horizontal asymptote. Or you may find a common denominator, and then you will see that is degree probably will be greater because -2x and 2x will be cancelled out. But this is also the good way to find just the limit. That means, remember, horizontal asymptotes are the limits at infinity. Okay? This is interesting. Find the vertical and horizontal asymptotes of the function sine over x over x. Yeah, this is a tricky question. Because you might probably say, we do have x in the denominator. Okay, which means x equals to 0 is not in the domain. And theoretically, I can't cancel out that x. Yes, that's the good note, Taren. That means, let me just finish. You can see, like, 0 is not in the domain. I can't cancel out. That means everybody will say, the vertical asymptote is 0. But we always have to be careful, and we have to check if the function as approaches 0 has really like unbounded values, like infinity. That means how function behaves at 0, how this expression behaves at 0 is really an infinity, because that's the point. We have to get infinity. Sine of 0 is 0. It's not a vertical asymptote. I mean, the important thing is this limit, because the behavior of the function at 0 is not infinity. We remember that this limit is 1. That means this completely like is taking the horizontal, the vertical line 0 is taking completely away of the asymptote. But Zach, what you asking? Sine of x, I mean, sine of 0 is 0, so it is not a vertical. I mean, I don't really know if that's the good reasoning. Sine at 0 could be 0, and we can still have a vertical asymptote. But the thing is, function at 0 is undefined. Okay? I can draw, we don't know, you don't know the graph, but function is not defined at 0. It's something like a little bit. It's something like that. Right? At 0, we do have an open circle. The limit is 1. We can nicely see the limit is 1, but no value. Yeah, that means it's not really an asymptote. And sine at 0, I can't even substitute 0 because it's not in the domain. Okay, that's when we don't have vertical asymptotes is none. That means that's not good, and this is not good. Okay, that's not good. That's mean now, what is the horizontal asymptote? And that's also a good question. Horizontal asymptote is 0 or 1? Horizontal asymptote is, of course, the limit at infinity. Sine of x over x. And what do you think? How this function behaves at infinity? It's no, it exists because what, yeah, x, we can see it's 0, right? Because the sine function, I can write something like really informal. The sine function like oscillate between 1 and -1, 1 and -1. But x is huge, it's like infinity. That means 1 over huge number or -1 over huge number is always 0. Okay, this is really, really informal notation. You can like think this way, because I shouldn't replace infinity. I can still put x. That's a little bit more safe. Okay, as we can see, comparing 1 to the huge number or -1 to the huge number, dividing by huge number, we always get a small number. Yes, we remember 1 over big, small, 1 over small, big, of course. Okay, that means this horizontal asymptote is actually 0, because the limit is 0. Okay, that means not 1. Oh, no, we don't even have the option none, which is good. Okay, that's interesting function. Okay, let's see. Oh, okay, slant asymptote. Do you remember? If the degree of the rational function is greater by 1 on the top, this is the case for the slant asymptote. That means we have to only divide 2x squared plus 0x. I can divide by x plus 5. And the quotient will be my slant asymptote. 2x squared divided by x is 2x. Now I will multiply back 2x times x, 2x times 5. 2x times x is 2x squared, but I will subtract. 2x times 5 is 10x, but I will subtract. That's 0, that's negative 10x. I can still divide. Negative 10x divided by x is negative 10. And then multiplying back, but you probably see I don't even have to finish this. I do have a quotient. This is the quotient, and that's the slant asymptote. Okay, always the quotient will give me the slant asymptote, 2x minus 10. Okay? Oh, this one is a nice question. I just need the x values that corresponds to the vertical asymptotes. That means who can tell me how many vertical asymptotes does this function have? 3. I mean, no, hang on. You saying x equals to 3? Or you answering my question? Because all of these values are the x values. Okay, like x equals to 3, x equals to 4. That means how many vertical asymptotes we have? We have 2 vertical asymptotes. Okay, what are the vertical asymptotes? Can you tell me the vertical asymptotes? X equals to 3, x equals to 4. Okay. And then you will circle that answer. Do you think this is correct solution? Of course, this is wrong solution. Do you remember what I said 5 minutes ago? You probably will watch the video again because you don't want to miss the easiest 5 points on the test. You're looking at the function, you have to factor out completely, which actually I did for you. The function has the product form, it's factor out. And you have to look for the common factors. If you can cancel them out, they are still numbers that are not in the domain, but they are not a vertical asymptotes anymore. That means they are only the potential candidates. And you can see this and this and this. That means I did cancel x minus 3 completely. Okay, only x equals to 4 will give me an asymptote. Okay, only this is a vertical asymptote. Okay, do you understand this? Please do not pick the option 3, I mean the x equals 3 and 4. Because when you can cancel out, the limit is just not infinity. Because as soon as the 0 is gone from the denominator, then it's not infinity. Okay, Please do not miss this type of question. Okay, what else? Horizontal asymptotes, maybe I can skip this one, I can skip this one. Okay, limit. Who can tell me what is this limit? Limit as x goes to negative infinity. I don't know if we can see. Negative infinity. And we have the function x minus 5 over square root of 4x squared plus x plus 1. That means who can tell me this limit? It's negative 1/4. Actually, okay, that's what I have. I do have x, and then I'm not interested in the other terms. And also, I am only interested, let me maybe do the product form. Let's assume that I factor out, because limits at infinity, I only focus on the leading terms, x and the square root of 4x squared. Okay, that's me now what we have. We do have, it's, yes, that's what, it's x, and then square root of 4 is 2, and now I have to simplify square root of x squared. But please note, we are at negative infinity. That means, we remember, square root of x squared is x if x is positive. Square root of x squared is still positive but negative x if x goes to negative infinity. And just the general statement is the absolute value for all x's, all the real numbers. That means that's important. That means this will be negative x. Cancelling out, I have negative half. Okay, please note always if it's the even root and the negative infinity. And also this is negative 1/2 is a horizontal asymptote, right? That's also an additional note. Okay, okay. Now we do have optimization problems, and I think that will be everything. Okay, I can skip this one. Let's do this one. You can check this question before the one before that I. Okay, that means we remember optimization, which actually was really nice this week because the optimization section was for extra credit, and actually you did really good. I did update the gradebook. That means you can definitely see now your actual extra points. Yeah, you probably see that your average is a little bit higher. I did update everything last night. Okay, just a small comment. Okay, that means optimization, of course, we have to find optimal solution, minimum, maximum values, minimum distance, maximum profit, minimum maybe surface area, maximum volume, depends what they're asking. That means let's see what question I have. What is a minimum vertical distance between two parabolas? X squared plus 5 and 6x minus x squared. Okay, that means I have to find a distance, but since it's a vertical distance, yeah, let me draw something. If I have one point, y2, let's say, and I have another value, y1. How can I define this distance? That means how can I define the distance between y2 and y1? Can you tell me this? Okay, I can, you probably know. Okay, what is the distance between 3 and 10? What's the vertical distance? What's the distance between 3 units and 10 units? Of course it's 7, right? That means how can I find the vertical distance? I can subtract the top value, yes. F of the top value minus the bottom value. Yes, correct? That means what I will do, I can possibly draw this parabolas. I don't know if we really need, but I would like you to know. Parabola x squared plus 5 is simply the parabola which is shifted 5 units up. Okay, the x squared plus 5. This one would be nice to find zeros. That means I will factor out x, and I see that x is 0 and x is 6. That means that's the zeros of the parabola. And I also see that the leading coefficient is negative. That means 0 and 6, and parabola up and down. Probably it's a little bit higher, but let's just leave it. That means this is my first parabola, y1, and this is y2. And now the vertical distance, I don't know, the minimum somewhere here, y1, y2. That means what I have to do, I have to find a vertical distance, which will be y1 minus y2. And let's substitute y1 is simply x squared plus 5 minus 6x minus x squared. X squared plus 5 minus x plus x squared, because I'm distributing negative, so x squared minus 6x plus 5. Okay, I did create a function that represents a vertical distance. Vertical distance between these two functions. Okay, now, because since we don't really have we don't have any restriction for the domain, I can accept any numbers, then I have to find local extreme values, and hopefully this will be a minimum. That means I have to find a critical points. I will find the derivative for x minus 6, and derivative is 0 if for x minus 6 is 0. X is 3/2. Okay, that means somewhere at 3/2. Okay. That means at 3/2, I hope minimum happens, because what I can do, I can actually test it. 3/2 and derivative. If I substitute 0, I have negative 6. Negative. If I substitute bigger number, I have positive. That means distance, the function behaves like that. Decreasing, increasing, and it is minimum, local minimum. Okay, that's when I did my first derivative test. Okay, that means actually, what is the answer? Actually, what is the question first? What is a minimum vertical distance? That means actually I have to find this minimum distance. Let me use maybe different color, blue. That means what I have to do, the minimum distance is simply defined at 3/2. And that was the distance function. 2 times 9/4 minus 6 times 3, 18/2 plus 5. Oh, who can do the arithmetic for us? This is 9/2 minus 18/2 plus 10/2, which is 5. Negative 9 plus 10, 1. Okay, 1/2. Actually, not bad number. 1/2 is the minimum vertical distance. Okay, that means just, but the same concept, the same idea you can always apply for any optimization problems. Find a function that you have to minimize or maximize, find the critical points, test it, and then depends what they ask. If they're asking for the actual minimum or maximum value, plug in that x to the equation that you found before the derivative. Okay. And you can, of course, I will really recommend you to check the extra quiz for the optimization, the quiz 7. Okay, and my little video about the optimization, the short video, because I'm solving quite good problems. Okay, let's see what else I have. Oh, I have a few true and false questions, and I think we can be done. But again, thank you very much for staying with me. It's quite a long session. Okay? And you can definitely watch some parts again. Okay, let's just go through some true and false, and we will be done. Okay, true or false? If f prime at c is 0, then function has local extreme values at c. Do you think it's correct? If the derivative is 0, which means c is a critical number, then we have local extreme values. You have to be careful. Do you remember the function that I gave you today, even explaining something? X cubed. Derivative of x cubed is 0 if x is 0. And do we really have extreme values at 0? We don't have extreme values. That means not always. Not all of the critical points will give me local extreme values. Yeah, this is the, oh, this is actually squared. I'm sorry. Okay, not all of the extreme values, I mean, not all of the critical points will give me extreme values. That means this is false. Okay, there exists a function f of x, which is continuous and differentiable. I like this. Everywhere, such that f of -1 is -2, f of 5 is 16, and derivative is always less than 2. That means this is probably the mean value theorem. But what we can do, we can try to plot these points. Let's see. At -1, the value is -2. And then I can write here. At 5, value is 16. That means if I will connect this, 16. The slope, because we remember slope of the tangent line is the same like the slope of the secant line, which I draw it. That means, what do you think? What will be, we can actually find out what is the slope. It's false. That means the slope of this line, because derivative means the slope, shouldn't be greater than 2. Could be 2 or less, but not greater. That means let's just find the slope of this line. Yeah, I think somebody answered, Karen answered that is false. Okay, rise over run. That means this is slope. And the slope will be, okay, what is rise? Can you tell me what is the vertical distance between 16 and -2? Mm, 18. Nobody is helping me, not good. And what's the horizontal distance between -1 and 5? 6. Oh, the slope is 3. And the slope supposed to be, that's the slope, supposed to be less than 2. That means this is definitely false. We don't have a function. Actually, when you will compute this, you will also get 3. That's the same thing. Okay, false. Assume that f of x is continuous on the interval from a to b. True or false? There is a point C in the interval AB such that f prime at C equals to f of B minus f of A, B minus A. What do you think? Is this correct? You have to be extremely careful. Where is the catch? Do you remember what I said? What are the conditions? It is false. What are the conditions for the mean value theorem? Oh no, we may have a point. Something is missing. What are the 2 hypotheses for the mean value theorem? Yes, thank you. Thank you very much. Function must be continuous plus differentiable. Okay, please remember, that's when I can't assume. Okay, I can't assume that we may have a point C, but then we will be not really, will be like a cusp or something. Yeah, I can have function must be differentiable. If it's not differentiable, it's wrong. That's we may have this case, which it will be wrong. And derivative will be not the same like the average rate of change. Okay, because that was missing. Okay, another one. If the function is a polynomial function, p of x over q of x, where p and q are the polynomials, and now the q at c is 0. That means c is the zeros of the denominator. Then function must have a vertical asymptote at c. Do you think it's true? Okay, let's see. We will have function x squared minus 1, x minus 1, x plus 2. That means the c values are the zeros, yes, the zeros from the denominator, 1 and negative 2. Again, good exam type question. Does this function has a vertical asymptote at 1 and at negative 2? Who can tell me this? Oh, come on. No. Okay. Okay, that means how many vertical asymptotes this function has? Only one. And it's happening this at negative. That's not a vertical asymptote because I have to factor out completely and I have to cancel out. Okay, that means this is no vertical